So let's take a look at the R examples. And the classification and regression tree cart algorithm is implemented in this rpart function in rpart package. So you first have to install this rpart package in your R session to use this rpart function. And this example is a kind of synthetic example, artificial example, showing that to see in this two-dimensional space how the decision tree can be built on a training set. So the training set, so this paragraph is explaining about the training set. The total 200 points were generated, and to make two groups, two classes, the first 100 points was shifted by 2 on x1 axis and by -2 on x2 axis. So I think in this code, we generate a random numbers from the normal distribution, so standard normal distribution. So the mean is located around here, I think 0 and 0. And to make one group marked as group 1, we shift first 100 points by 2 on x1, so by 2 x1, so we move the mean, the center of the first group from here to here and -2, so from here to here. So we make class 1 around, so the center is around here, and we make class 1, and the remaining 100 points will be marked as the class 2. So there's a little overlap between these two classes, and this R code is to generate this training set. So let's do this together. Let me copy these whole R comments and then paste it into the editor, R editor. And here's N is to specify the number of points for each group, and this one is to generate the random numbers from normal distribution using R norm function. So because I'm gonna make 200 points on two-dimensional space, so what this function does is generate 400 data points from the standard normal distribution and make using that numeric column by specifying the two for the number of columns, we can generate a two-dimensional matrix. So there is no correlation. So this first column forms a normal distribution, and second column is a normal distribution. So there is no correlation. Correlation is 0. And save that into X, and then this one is to make a class 1. So the first from 1 to 100, the first 100 points, and it's their x-axis coordinates will be shifted by 2 on x1 axis and then -2 on x2 axis. So this was just to shift the first 100 objects. After that, this code is to generate class labels. So using the lib function, we repeat 100 times, we repeat 2 100 times, and then make a class label column. Then this one, using the data.frame function, we make a data frame where the first column is the x1 axis, right? x1 axis, x2 axis, and then class labels. And then you can see that by scrolling down the points, and then from the class 2, the coordinates are a little different, right? So you can see the difference from this 101 data point, right? There's a little, we can notice even from these numbers themselves, we can notice that there's a difference between the first 100 observations and the remaining 100 observations. So after that, we're gonna make a plot using this plot function. The first input argument is the x1 coordinates, and then x2 coordinates, and then x labels, y labels, and then the type. If we specify type as n, then actually nothing appears on the plot, as you can see from this figure. But by doing this, this panel remembers the coordinates, but just doesn't show the points because we want to mark each of the points as numbers using this point function. So the first input argument is the x coordinates and y coordinates, and this PCH is the type of mark that we want to plot on this two-dimensional space. So let me run this code, then we can visualize the class 1 objects, and then the other part is the class 2 objects. Okay, so this code is to generate an artificial data set, and then in the same way we can also generate the test set. So this one is just to specify the number of test sets, number of test objects, and then the R codes are the same as before. Using this rlum function, we generate random numbers and then shift the first few observations by 2 on x1 minus 2x2, and then generate a class label and make a data frame. Okay, this one is also same. So let me just copy and paste and run this one just to generate a test set. Okay, after that, sorry. After that, what we're gonna do is we will train a decision tree using rpart function. This code does that. So I'm gonna do the same thing. I'm gonna copy and paste these commands and then run in my R session. So as I told you just before, we have to install rpart package first. So if you don't have this rpart package in your R session, please go to package tab and then click this install button and type rpart and then install this rpart package. And I already installed this one. And then using this library function, attach this rpart package in your R session. Then now you can use this rpart function. Rpart is short for recursive partitioning and regression tree. So as you can notice from the name of cart is short for classification and regression tree. So actually we can use this cart algorithm for the regression problem, but I didn't explain about it. It's just the mechanism for building a tree and pruning a tree is the same, but instead of that impurity measure, such as the information entropy, we use the difference between the predicted value and true value. We make the split to minimize that quantity, but I didn't explain about it in detail because we are playing within the context of classification. So actually this rpart function also can be used for prediction and regression as well. So the first input argument is the formula. So we first specify what the response is, and actually the response is the class label, the third column in my training set. And I'm going to use the remaining column as my input variables. So x1 and x2, they will be used as the input variables. And then this one, actually, you really don't have to exclude this one. But so let me correct this thing. So instead of actually this part means that I'm going to exclude the third column, but we really don't have to do that because the second input argument is, as you can see from here, an optional data frame in which we interpret the variable named in the formula. So x.train is enough, so please correct this. And then method is class. So it means that I want to do a classification by specifying this one. So let me learn this part, this line to build up the classification tree, and it will be saved in this x.rp r object. And then if you click this one, you can see this text-based decision tree. And let me give you a brief explanation about this expression. So the first one is the number of node number. So there are 3 nodes, and second is the split, and third information is, I guess, the number of observation and loss and y class label and the probability. So in the root node, this one, the first node is root node, and there are 200 objects, and the loss is 100 because its class label is specified as 1. So the other class 2 objects, they are misclassified based on this expression. And in this root node, the probability for class 1 is 0.5 and class 2 is 0.5. It's just the proportion of each of the classes. And that this root node is split into two child nodes, node 2 and node 3, by this split. If y is less than 1.5, then the data points satisfying this condition goes left, and then in that child node, there are 100 objects, and this one is loss. So loss is 0, and the class label, so it's kind of perfect classification. So let us take a look at the plot again. So oh no, so okay, I see. So I didn't make a correct, I'm sorry, I didn't make a correct classification tree. So in this code, we have to exclude the class label, the class label column, right? So let's go back to the help, and then I don't know why, but actually in the previous in this tree, actually the class label itself was used as because I didn't specify the third column as a factor type, so it was used for the predictor variable, independent variable. So we have to exclude in this formulation, in this type of code, we have to exclude the third column. Then let me learn again. Then this R part is, yes, it's more, how to say, it's more complex. The structure it has, this tree has more complex structure. So again, that the root node is split into two child nodes, node 2 and 3, by this splitting criteria condition. And then this node 3 is also denote I'm sorry, also split into two node 6 and 7, and node 6 is split into two child nodes 12 and 13. So if you want to take a look at if you want to see this tree structure as a plot, then you can just simply use actually this one is not in the lecture slide. You can use the plot function, and then its input argument is the decision tree that you just trained, x.rp, and learn that one. Then actually this command just shows the structure only, and to write on to write the class labels and the split criterion on this figure, you have to learn additional command, which is text, and its input argument is same as before, x.rp. Then you can see that you can see this decision tree. So this one is root node number 1, 2, 3, I guess, and then 1, 2, 3. 3 is split into two things, 6 and 7, 6, 7, and 12, 13. Okay, and then the lines indicated by this, what is that? This star mark. This one indicates this node is a leaf node, terminal node. So yes, this one denotes the terminal node. So you can see the structure of decision tree, train the decision tree in either in this text format or in this graphical format. Okay, and then what is this one? X dot train. The third column of x dot train is true class label, and you can use predict function, just like what we did in the logistical regression, to make a predicted class. So its input argument is train the tree, and then you can put the x variables only in the training set, and type class is that means that it means that I want to predict as a class label. Then by learning from P to this thing, you're gonna get the predicted class, and using table function you can make a confusion matrix. Yes, this one is a confusion matrix, and there are 16 objects that are misclassified, and I'm gonna save this confusion matrix into the R object, which name is A. And then this one is training error because I'm gonna skip the explanation about this one. This diag function is to extract out, the diagonal elements, and then make the summation of diagonal elements, and then subtract from the whole observation, and then divide by the. I said I'm gonna skip the explanation, but I'm explaining. Yes, so this one is to calculate training error, and in the same way, likewise, using the test set, this one is the true class label of the test set, and we make the prediction of the test set using the training, using the trained, the tree, and then make a confusion matrix for the test set, and then calculate the test error. Okay, let me take a look at this confusion matrix for test set. Not bad, I think. Yes, and so that's everything about the building classification and regression tree based on this two-dimensional data set. So what you can do is very simple. You can simply install this rpart package and then use this rpart function to build a classification tree. Okay, and then this slide is just to show I explained about this one. To get this kind of figure plot, you can use the plot function and text function. And actually there is no code to generate this kind of figure, but it's just to show the decision boundary by this decision tree. So first split, this one, the first split is corresponding to this line, right? And that is, again, let's take a look at that. Oh no, here. Yes, I'm sorry. So because the split criterion is x2 is less than minus 0.7 is around here. So this one is the first split, right? And then what is that? The x1 is greater than 0.93. Yes, so this one is the second split, this one. And then what is that? X2 equals to minus 1.6. This split is corresponding to here, and this split is corresponding to this one. Okay, and then class labels are assigned each of the leaf node. So actually the decision boundary is formed in this way. Okay, and based once it's so how do I display this decision boundary is that once I trained this decision tree, what I have done is I generated a uniform random numbers on this two-dimensional space, and I consider them as a training the new data points to be predicted. So I put all those randomly generated points in this trained decision tree, and then make the prediction for those, and then for the class 2 I make this color, this little gray color, assign that color to the data points predicted as class 2, and then a little darker points. I used a little darker points to display those points predicted as class 1. So just to see this decision boundary. It's just for your information, actually, because this data set is two-dimensional. We can visualize the decision boundary on this two-dimensional space, but even though we have even one more predictor variables, then we cannot visualize. So it's just for your information that to show that how this decision tree forms the decision boundary. Okay, and this one is a real data set, music data, and let me read this paragraph. And actually this data set was that this one came from a class that I took when I was a graduate school, when I was a graduate student. So this data has a this data set is quite old. So this data was collected by Dr. Cook. Actually, she is one of the quite famous statisticians in this world. And then she is a professor of statistics department at Iowa State University. Actually, I went to this university for my PhD degree, and I took her class. And then actually, when I was taking her class, she gave us this data set for the practice of the classification. So she extracted some data from her own CDs. Actually, nowadays we don't use a compact disc anymore to listen music, but at this time we used we used the CD players to listen music. And so using her Mac, and she read the track into the music editing software, which name is Amadeus 2. Yes, quite old. We don't use this software anymore. And saved the first 40 seconds as a WAV file. And WAV is an audio format developed by Microsoft and commonly used on Windows, but it is getting less popular. Anyways, she converted her music as a WAV file, and these for the first 40 seconds. And these files were read into read into R using the package tuneR, and this converts an audio file into numeric data. So that you can actually, this data set can be obtained from the iCampus. Actually, I already uploaded this data set in our R iCampus, and so you go to the class site of the iCampus, and then you click this title, this tree, and there is a link to, in this page, there is a link to get this music.csv file. Okay, and I already have one in my directory, and that looks like this one. I think the first column is the title of the song, and the second column is the artist, and then the third column is type. So there are two types of music, rock musics and then class musics. So this one is the class label, and there are one, two, three, four, five independent variables, and that are these five independent variables: L, VAR, L, AVE, L, max, that are average, variance, and maximum of the frequencies of the left channel. Actually, this data set was obtained from only the left channel, actually the right channel. There must be a little difference between left and right, but this data set was from the left channel only. And RF, E, and R, I guess it's kind of energy, an indicator of the amplitude or loudness of the sound. So this one indicates the loudness, and then L freq is median of the location of the 15 highest peak in the period gram. So because the song is a kind of sound, what I'm guessing, I'm not expert in the sound, but what I'm guessing is this one is kind of time series data set. So it's kind of signal on the time axis. There must be some, I guess, I don't know what it is, but it's like a signal here, and then during the 40 seconds, and then take the variance and averages and maximum value, and then loudness. I don't know how do we get this thing, but and then median of the location of the 15 highest peak. So it's actually from this raw data we extracted out five independent variables. This procedure is called, this one is just for information, this procedure is called feature extraction. Or feature generation, or feature, yes, actually we don't use this raw data itself. Instead of this one, we use these summarized information for each of the songs, right? So typically in classification task, because we have to have the features, independent variables, predictors, they are the same. And I told you about this at the very beginning of this class. And the typical procedure is from the raw data, especially this kind of time series data. What we do is we extract features. After that, based on that feature, this is what we are doing now using this music example. We build a classification model. But nowadays, such as the recurrent neural net, I'm not sure if you heard about this name. This is a type of neural network, and these days, or CNN, convolutional neural network. Actually, this one is kind of the state of the art method, the very recent method in classification or prediction regression. And in this area of the classification method, we really don't have to go through this step. We can just directly build a classification model if we use this kind of uh, classification method. This one is just for information. It will not appear. It won't appear in your exams. It's just for your reference. Just for your information. Recurrent neural net and convolutional neural net. Then we can skip. We can skip this step. But even though we skip this step, it doesn't mean that it's always good. Sometimes it's bad. Sometimes if we extract some features, there are some good points by extracting features. Anyways, there are 5 independent variables, 5 features, and there are 54 songs and 2 classes, classic and rock. So this code is to train a decision tree based on this music data. And again, let me copy this part and paste it into, let me erase everything in my R session. And paste all the comments and then attach R part package and then bring that music.csv data into my R session, and then using this R part function, I want to build a decision tree. This one is formula, and the reason that I typed here independent variables features explicitly is because there are another columns that I do not want to use as a features. So d.music. Okay, I'm gonna use the last 1, 2, 3, 4, 5, 6 columns, and I don't use these 2 columns. So if I use a dot instead of this one, then it means that I want to use these first 2 columns as well for my independent variables. So we have to specify explicitly what the features are here. And then the data is music, data music, and method is class. Okay. So this one is formula, specify data set, training set, and I want to build a classification model. This third argument means that. Then by learning simply by learning this single line, you can train a decision tree very quickly, right? And then using these 2 columns, you can see the decision tree here. Okay, so just for your information, if you click this export and then copy to clipboard and then control the size of the plot and then copy plot, click this, and I recommend this option meta file. And if you click this copy plot, this figure is saved in your clipboard, so you can paste it into where you want, such as this PowerPoint slide and your Word. Okay, so that is for your information. And I want to predict using this trained decision tree using this predict function, and I put the x variables only here, and this m.rp is the trained decision tree, and the type of prediction is class. And then this one is the predicted class that is stored in the pred.y. And using table function, you can make a confusion matrix, right? Okay, only seven classical musics were misclassified as raw. So accuracy seems good. So let's calculate the accuracy. Some diag CFM over, am I right? Some CFM. Okay. Diag Oh, okay, there's no CFM. So the accuracy is 87% for this training set. Okay. Okay, this slide shows that. That's everything. So what in what we have done just before in this code, actually we didn't go through the step for dividing a data set into training and test sets. So actually we first have to know about how accurate a decision tree can be built based on my training set. We first have to go through the step for dividing the data set into training and test set, and then train a decision tree based on training set only, and then test your trained decision tree based using that the remaining test set. Just like what we have learned, what we learned in this model assessment class. Okay, in this model assessment class. That's everything about the decision tree. So it's been about 36 minutes for this class, but I'm gonna finish at this moment uh, because we have done all about the decision tree. So we're gonna see you again with a different topic in the next class. I will see you again. Thank you for your attention.